as we have three disparate topics, each of which will raise very interesting questions. So what I'm going to propose is that we actually give each speaker the half an hour to divide 20 minutes presentation and 10 minutes Q&A. I'm David Newbury, I'm the moderator and also the last speaker. And the themes that we were presented to organise this conference cover a wide range of things, as you can see: smart grids and appliances, technology and regulation of isolated electricity systems, very topical issue in this state, and finally integrating the renewables into the grid. So if we look at the challenges facing the transmission system with the evolving pattern of technology, the transmission system, I would argue, is already pretty smart. The big challenge is for the distribution networks, which in the past have been fairly dumb and need to clean up their act and get on top of things. And a whole range of technologies are available. The issue is, how do you put them in place? How do you encourage the management to want to put them in place? And what will they deliver? So are we evolving from distribution network owners to distribution service operators? That's an issue you may touch on. This is the sort of challenge that are faced if you put a bunch of electric vehicles on an existing peaky pattern of demand. You need to invest a whole lot in transmission and distribution assets. If you can shift that load to the off-peak, then you can completely avoid that investment. So you need to signal when those EVs will charge. The same problems will arrive with heat pumps. If we look at isolated systems, we have the expert who can tell us about the problem of managing supply and demand when you've got really small and isolated systems, and what role various options like demand-side management, storage, whether directly in electricity or indirectly in heat, can deal with that. And in particular, when you connect wind, what sort of contract do you sign to them? Fortunately, communication technology and computing power means that many of these things can no longer be required to have individuals act, they can be devolved. And finally, when we come to integrating renewables, most of them are intermittent, the ones that are likely to be most important, like wind and PV, and they need backup. That backup has a very variable demand, and financing that very unpredictable demand can be a challenge. So that's a problem. The problem of what is the best form of support for this renewable technology that we want to develop, that's another issue. So I'm going to look at wind in Europe in particular as a leading example of that. So we have three speakers, three topics. Scott Samuelson received his PhD in mechanical engineering from UC Berkeley, and is an expert on advanced fuel cell technology. No doubt we'll hear something about that. Mira Kola is president and CEO of the Alaska Village Electric Cooperatives, and has been in rural electricity business for the last 34 years. So I'm sure she knows everything there is to know about isolated systems. With that, we'll go straight into our first speaker, Scott Samuelson.
Thank you, David. In this particular presentation, I will be addressing a number of the issues that David just presented. I'll be doing it in the context with an emphasis on fuel cell technology, also as David indicated, and it's entitled The Evolution of the Electric Grid. I want to begin with this diagram of the electric grid with the central generation on the right and the distributed generation on the left, with aspects of it that we all recognize. The point I want to make on this slide is the dependency that we have on combustion today, both at the central plant level as well as microturbine generators and gas turbines in distributed generation. If we also look at our dependency on combustion for transportation, we find that we're equally dependent upon combustion there as well. This particular powertrain is the electric powertrain that we're moving toward in hybrid technology with a hybrid battery and electric motor. You can see that it provides an overall efficiency up here of 32%. It does demand that we process about 1,000 pounds of air per tank full of gasoline, and from that we'll remove about 200 pounds of oxygen from the atmosphere. And it gives rise to these major products of combustion: carbon dioxide, water, and nitrogen, and of course the pollutant species, oxides of nitrogen, carbon monoxide, and hydrocarbons. Combustion today is actually responsible for upwards to 80% of the total power generation in the world, whether electricity generation or the propulsion of the automobile. It does take fuel and air, and it does process it through a variety of steps that include the combustion chemistry, and then mechanical devices such as pistons and turbines, generators, to eventually produce the electricity for either our electrical needs in terms of room lights, as we have here, or the electrical needs that we have for this new hybrid automobile technology. You can almost intuitively feel that there's going to be limited efficiency due to the mechanical systems that are part of this process. And then we all know that due to the combustion chemistry that we have the emission of pollutant species, that list that we just went through. As an alternative is the fuel cell, and its attributes include one step from fuel and air to electricity, electrochemistry, and this gives rise, again, intuitively you can feel, to a high fuel to electrical conversion efficiency, no pollutant emissions since we do not have the combustion chemistry, instead we have the electrochemistry, and then it's also acoustically benign, which is attractive for many applications. It does mean that we are directing more attention to fuel cell technology in the area of mobile fuel cells and stationary fuel cells. And we're starting to see that fuel cells will play a pivotal role in the evolution of the grid in the future. We have these attributes, for example, that we just went through for fuel cells, mobile and stationary. And then due to the application, there are additional attributes for each. For example, in mobile fuel cells, we have 4 additional attributes that I'll mention. And for stationary, just to be symmetrical, 4 additional attributes specific to the application of these 2 fuel cell types. And I'll go through this in more detail here in a moment, but let's just look at what a fuel cell combines and encompasses. This is what it looks like by way of a cartoon, a little bit like a battery. Its principal part is the heart of the fuel cells, the electrolyte. And then on one side is an electrode we call the anode, and on the other side another electrode we call a cathode. Fuel enters into the anode port, and oxygen from air enters into the cathode port. The fuel reacts at the surface of the anode to give up a proton as well as some electrons. That electrolyte says, you know, proton, you're welcome to go through from left to right. I welcome you, but the electron, need to find another path. Now that's fortuitous for engineering because we can take that electron and drive a load, let's say a light bulb. The electrode comes back a bit spent, as you would expect, to the cathode side, but still enough energy to oxidize the oxygen from the air to produce an oxygen atom that then combines with the proton to form our product of water. And then out of the exhaust comes the water along with the nitrogen that went in with the air. This particular kind of fuel cell has a chemistry, you can see it, we just went through it, and it's called a proton exchange membrane fuel cell. It also operates at a specific temperature, right around 90 degrees Celsius. And there are other types of fuel cells, and we'll look at those in a moment, but this one is particularly attractive for the automobile because it has a reasonable temperature of operation, and we can also turn it off and on at will, so it has a dynamic capability that is very attractive. If we now look at the application to the automobile, we come back to our gasoline-powered hybrid, and let's initially replace the gasoline with hydrogen, and replace the gasoline here, of course, with hydrogen. What that does right off the bat is to remove any carbon or hydrogen containing species in the products. For example, the carbon dioxide goes away, which is what we want for climate change. And for urban air quality, we'd like to get rid of a few of these pollutants, and hydrogen takes away the carbon monoxide and the hydrocarbons. So just that step is attractive, and as well as providing, of course, our goal towards fuel independence in the countries around the world. If we take the next step and replace this reciprocating combustion engine with a fuel cell here and under the hood, we now have the fuel cell hybrid vehicle. And I want you to recognize that this is the way the vehicles are evolving. They're evolving as hybrid, battery electric. They're electric vehicles, but they have the longer range. What this does is to increase this efficiency by actually a substantial amount, more than doubles that efficiency. It reduces the amount of air we must process and the oxygen we take out of the atmosphere. And then over here, it removes the remaining pollutant species that we are looking to preclude for improvement of urban air quality. So that in a nutshell is the fuel cell vehicle. You can imagine that under the hood we have something that looks like this, an engine, not a reciprocating engine, but a fuel cell engine with hydrogen as the fuel, producing along with air, direct current to drive the motor, and then the exhaust we now know is made up of water and nitrogen. What this is looking like are three examples you see here, a product from General Motors, Toyota, and Honda, all of which have been undergoing road testing for up to a decade, depending upon the vehicle. We want to identify those three attributes we talked about earlier, and remember I said that it adds another 4 depending on the application. In this case, for mobile fuel cells, we have the additional attribute of no tailpipe emission of carbon dioxide, a 400-mile range, which is equivalent to what we expect today as the public, refueling under 5 minutes, again, something that we're used to and want to retain. And then we're seeing this coming out in a range of fuel cell sizes. As far as mobile applications, it's not only automobiles, but also buses. And we're starting to see now more and more fuel cell buses being deployed around the world. And then other applications we call specialty vehicles. This is a forklift truck where batteries are being replaced by fuel cells in order to provide much faster charging time and also longer use per charge. On a commercialization basis, this is actually commercialized today. It's a very popular application for distribution centers, for commercial applications, and for the government. On the automobiles, we're looking to 2015, just 2 years from now, for the retailing of automobiles in select markets throughout the world. Well, this is the list of the attributes. We've just talked about hydrogen powered. Let's go to natural gas powered to give you a feel of that application. And here we're really talking not about a mobile application, but a stationary application. And for that, we need to derive our hydrogen from a practical source. And that practical source is typically natural gas, which through a reformation process provides the hydrogen. On the electrical output side, we are not quite accustomed to using DC today, though I think we will be more in the future. So we go through an inverter or power conditioner to produce AC. And this basically then is the fuel cell for the stationary application. Here are those basic 3 attributes that we introduced at the beginning, and the additional 4 for this application include high quality heat, because in a distributed generation application, we wish to operate this, if possible, as a combined cooling, heat, and power. No water consumption, one of our major goals in the future of producing electricity. Reliable 24/7 operation, baseload operation. And then a means of maintaining and controlling power quality, which is becoming much more important to the consumer. Well, here's our diagram again of the fuel cell, and you see the proton exchange membrane fuel cell. I promised you other fuel cell types, and here they are. Phosphoric acid, fuel cell number 2, molten carbonate, fuel cell number 3, and then the solid oxide fuel cell number 4. And you can see that the chemistry is in some cases similar to the proton exchange membrane, and in other cases quite different. And it's that electrolyte here and the attendant chemistry that causes a variation in these fuel cell types. We call them types. And if you look over here, you can see that the temperature varies substantially from the relatively modest temperature of the automobile proton exchange membrane fuel cell to upwards to 1,000 degrees Celsius for the solid oxide, another distinguishing factor of these fuel cell types. And intuitively, you can start to feel that these up here, once you turn them on, you don't want to turn them off. And you're right, these want to be base loaded, so they would not be applicable to an automobile, for example. Here are the manufacturers for these with respect to the major manufacturers today in the world deploying these systems commercially: Clear Edge Power, Fuel Cell Energy, and Bloom Energy. If we look at the deployment in the commercial market, I take California as an example, you can see up in the right the table that shows a very attractive distribution of applications, and from an economic point of view, you would agree that this is attractive in order to get traction for a product, to have a variety of market segments engaged and have a variety of risk values engaged. Up here you can see about 61 megawatts deployed in California. That's actually more like 80 megawatts today, and the red dots in the map represent locations where these facilities have been located. Here you have a risk-adverse hospital, a St. Helena in Northern California. That's a 400 kilowatt phosphoric acid fuel cell recently deployed. Here you have a grocery store in San Diego, another 400 kilowatt phosphoric acid fuel cell. In the outage that went from Arizona through Southern California in the September of 2011, this fuel cell had just been installed. It went into an islanding mode during that outage, retained services for the community of food and other supplies, and precluded the disposal of all the perishables in the store, which would have had to occur after 4 hours of the outage. In Hurricane Sandy, 23 of these units, all of the units in the footprint of Sandy, remained in operation, island, and provided those services to the community. And this has caused a major uplift of attention in Congress with respect to the utility of these systems, as well as to microgrid technology. Another application is another risk-averse application at Northridge campus of Cal State University. This is a 1 megawatt deployment of molten carbonate fuel cell product with waste heat recovery, as we've seen already. This is an application in Ontario, California, a relatively interesting one and relatively new. It's 2.8 megawatts, and it's operating on biogas, so it's actually producing renewable heat and renewable electricity. And today, it's the largest biogas powered deployment in the world. Now, if you notice up here, we can't quite see it anymore, but between natural gas and biogas, we have a pretty even split of operation in the state of California. So this is a very popular application. Another example is a 2 megawatt solid oxide deployment at Caltech Institute of California Institute of Technology. And if you take these combined, this is Clear Edge Power that began commercialization in 1990 with the phosphoric acid fuel cell. This is Fuel Cell Energy with the molten carbonate, began commercialization in 2003. And this is Bloom Energy, which began commercialization in 2009 with the solid oxide fuel cell. Coming back to our map of the grid, we're seeing deployments here in distributed generation at industries, at hotels, hospitals, universities, at the wastewater treatment plant with renewable operation. Those are the commercial products that are now being deployed in California and other locations in the world. We also are starting to see a commercialization of fuel cells in residential applications. That's very new. And we think in the future that we'll see fuel cells deployed on the utility side of the meter in order to provide grid support at the pinch points between transmission and distribution legs of the utility. We have a special name for this. We call them Tiger stations, for Transmission Integrated Grid Energy Resource. And up until recently, it's been a figment of our imagination that this might occur someday. But here's some evidence of it occurring. This is in Korea, which has become very, very proactive in the deployment of fuel cells. Over 10 years, we have 80 megawatts deployed in California. Over 4 years, over 200 megawatts deployed in Korea due to policy that encourages this kind of technology. This is the largest fuel cell power plant in the world at 11.2 megawatts. But we're on the cusp of soon to be the largest fuel cell power plant in the world in the United States, in Bridgeport, Connecticut. You can see it's under construction at 15 megawatts. And then we have will be the largest fuel cell deployment in the world, 59 megawatt deployment now in construction in Korea. All examples of this Tiger concept on the utility side of the meter. Well, it looks like we haven't gotten very far down our list, but we actually have. We've talked about 24/7 baseload, virtually zero emission of criteria pollutants, and we've talked a little bit about the biogas operation. I want to give you a bit more on that. Let's just look at a wastewater treatment plant and use this as example number one. This is the manner by which our sewage and garbage disposal products are processed with different types of processes here, but primarily a digester that creates a biogas but needs heat. And the heat is typically provided by a boiler operated on the biogas, but also on natural gas to complement that. And then we have electricity coming in from the grid to support this overall operation. A very exciting and expanding market in the world is the use of a fuel cell in this application to replace the boiler, whereas now the heat from the fuel cell for free can provide the heat to the digester, and then in addition you're getting AC power to support the plant itself. And we showed you a moment ago this example of this 2.8 megawatt system in Ontario. So this is example number one. Example number two is fascinating to me. This is a privately owned onion operation, the largest in the United States, in Oxnard, California, where the family